All right, so we will now move on to a second practice problem or a second class exercise. So here we are going to sort of transition from a one-dimensional real line, representation of spatial locations to a two-dimensional, representation on a circle. So I'm going to read out the problem, and then we will sort of step by step start to resolve the issues that arise with spatial dependent structure in a two-dimensional space. So consider a real estate market for a circular city with n equally spaced homes that are located along the city's circumference of k units. Okay, so what we are talking about is a circular city. So I'm going to draw a circle, all right. And now we have n equally spaced homes. So the circumference of this circle is k. So, and there are n homes which are equidistant from each other. So that means that there is going to be, homes or houses placed on this circle at a distance of k by n along the circumference, as we go. So let's call this as location 1. So, the first star that I've drawn is location 1, and I'm gonna go in the, in the clockwise direction and keep sort of adding a dot or a location for a home every k by n units apart. Okay, of course I'm gonna do it with approximation because I don't know n, I do not know what is k by n. It's just a schematic, not to scale representation on your screens. So say this is home 1, home 2, equidistant to 2 is home 3, then we have 4, we have 5 and 6 and so on and so forth till we get to a point where we have a home here called the nth home. The home price at each location I is denoted as PI. So the price of a house that is, that's the market that's kind of observed in the market, in the real estate market of this circular city is, indexed by its location. So at location 1, the price is P1. At location 2, it's P2. At location 3, it's P3, P4, P5, P6, and all the way till Pn. Okay. Now, these prices are assumed to be correlated with prices of homes that are I's first order neighbors. Okay, so at any location I look at the location on the right to it. Okay, so one step in the clockwise direction, one step in the anti-clockwise direction. So for every I will look at location I minus 1 and location I plus 1. So I'm going to say for location 2, I'm going to say that the price P2 is correlated with price at location 2 minus 1, that is P1, and location 2 plus 1, that is P3. Okay, and obviously for 3, of course, it's going to be 3 minus 1, that is P2, and P3 is going to be correlated with 3 plus 1 at location 3 plus 1, which is P4, right? So this is how the correlation structure is going on in space. Now, although this is all quite, this is a model, and of course, it is a representation of what happens in the real world. All it is trying to say is that the real estate prices in the real world can be represented by a situation where they are highly correlated with immediate neighbors and not so correlated with those who are farther apart. Okay, so maybe you can say that homes in a particular locality can be considered neighbors, and homes in different localities or between localities are non-neighbors, right? So that kind of a situation is what this particular stylized setting is providing us. Okay, we define this set Ni, which contains the neighbors of I. That is, Ni is a set which contains I minus 1 and I plus 1. So neighbors of 2, neighbors of, you know, the home or house at location 2 are houses at location 1 and 3. Neighbors of you know, the house at location 3 are the houses at location 2 and 4. What about you know, the neighbors of you know, of house at location 1? What about location 1? Well, here the neighbors are n and 2. Okay, so because it's a circular city, instead of a real number line where n only had one neighbor, now it also sort of has the second neighbor, which is house 1. Similarly, the set for, you know, of neighbors at location n will be location n minus 1 and location 1. Okay, and so on and so forth. So basically we can define this set for that contains neighborhood houses as Ni. It's a very efficient sort of a efficient mathematical notation, I would say. Okay, so needless to say, for the given case study, that Ni, number of elements in each set Ni is 2, which is correct. So you know, we have I minus 1 and I plus 1. So we have 2 elements in Ni, which is fine. And if j is in Ni, then I must be in Nj. That is, if j is in the neighborhood set of I, then I must be in the neighborhood set of j, which is also correct if we look at the examples that we have written out here. Let the home prices Pi be drawn from a normally distributed random process such that expectation of P is the population, you know, mean mu P, and the covariance structure, which is the spatial dependence structure, covariance Pi Pj, where I and j are locations I and j. So we have a spatial dependence structure which exhibits correlated prices with first order neighbors, something that has been written down in English, right? So whatever is written in English simply is translated with mathematical you know, notation. So covariance Pi Pj is sigma squared if I minus j equals 0. That is, variance at a location I, that is, variance of Pi is simply sigma squared for all I. Okay, all I in 1 to n. Okay, covariance of you know, of prices between locations I and j, if they are an immediate neighborhood, is given by sigma squared lambda, and lambda can be between -1 and +1. So now we are allowing for negative spatial autocorrelation as well in the two-dimensional space, right? So of course, needless to say that this circle represents a 2D world, two-dimensional world. And for homes that are farther apart, there is no correlation, right? So we've discussed this now. Again, this is we've discussed this earlier. The first query is write down the full variance covariance matrix for the given random process. Okay. So I'm going to have to write down the variance covariance matrix for the given random process. So I'm going to do that. So I've been given this this vector of prices P. This vector of prices P, which is nothing but P1, P2, all the way till Pn. All of these are distributed jointly, right? It's a random function. We are working with spatial data, something that we have covered in one of the earlier lectures. So we are working with a jointly distributed normal, distribution, right? So they are jointly distributed normal random variables with mean mu p, something that is provided as information, and the variance covariance given as some sigma p. Okay, so I know that my my p is a n by 1, so n by 1 vector, so there are n rows and 1 column, right? So p1, p2, p3, p4, p5 till pn, right? And so mu p, which is the expectation of each p, is nothing but n by 1. So this itself is a vector. And the variance covariance matrix is going to be a n by n matrix because it should contain all the variance values and the covariances, right? So this is something we have seen earlier, that for a vector which is n by 1 size, the variance covariance matrix is n by n size, right? So variance of P, where P is a n by 1, is given as sigma P. So I'm going to draw a n by n matrix. So I'm going to have n columns and n rows. So let's say each row represents i's. So I equals 1, 2, 3 all the way till n. And columns represents locations j so far as the covariance structure goes. Okay. So if for the first cell of this variance covariance matrix, when I equals j, that is I minus j absolute value is 0, then the variance covariance, the covariance structure will tell me that the diagonal element will be sigma squared. Similarly, for all diagonal elements, when I and j are equal, exactly equal, what I'm going to find is a sigma squared value at all diagonal elements. For the first off diagonal element, where I equals 1 and j equals 2, we can go back to our covariance structure and write this value to be sigma squared lambda. For the third position, however, 1 and 3 are 2 positions apart, no correlation, we will have a 0. So we will have a 0 at 4, at 5 and keep going. At location n, we know that in neighborhood set of location 1, n is 1's neighbor. It's in fact the first order neighbor of 1, right? So 1 will have a spillover from and to location n and location 2. Okay. So the value of this off diagonal element in the first row and nth column of this variance covariance matrix is going to be sigma squared lambda. Okay. Similarly, when we move to I equals 2 and j equals 3, I'm going to have sigma squared lambda. At 3 and 4, sigma squared lambda. So you can see that the elements that are right, besides this element, this diagonal elements, sigma squareds are going to be sigma squared lambda. Now variance covariance matrix is a symmetric matrix, so you're going to have sigma squared lambda, 0, and so on and so forth, right? So you're going to have sigma squared lambda, sigma squared lambda. Okay. Now, just like you have, n is in the neighborhood set of 1, 1 is in the neighborhood set of n. So we will have a, in the spirit of symmetry of the variance covariance matrix, the element in row n and column 1 of sigma, of variance covariance matrix sigma is going to be sigma squared lambda. Everything else is going to be zeros. Okay, I'm going to have all these things are going to be zeros. Okay, so this is the first query that this matrix that I've written down here is the variance covariance matrix of the given random process. I'm going to write it again just so it is absolutely clear. So it's n by n, all the diagonal elements are sigma squareds. Okay, the off diagonal elements, the first order off diagonal elements are sigma squared lambdas. Okay. Okay, and then the second order diagonal elements are zeros, except for this aberration between 1 and n, which happen to be neighbors. So I'm just going to fill them in. Okay, I'm going to have 0, 0, and then sigma squared lambda. Okay, I hope this is absolutely clear. So you should definitely write this out by yourself so that it becomes very, very clear what is going on here. Okay, so now we have this spatial dependent structure condensed in this n by n matrix sigma. So let's take the next step. All right, next it says, say you have a sample, is sample meaning realizations at each value on that circle, where P1 is 1, P2 is 2, and so on. So the value of Pi is simply I, which is the value of the home at location I is just I. So somehow the location itself is an indicator of value, right? So it's a specific, again, a very specific example. Then deduce the consistent estimator of omega p, mu p, which is the population mean, and those for the 95% confidence bands of mu p. How does your estimator depend on spatial heterogeneity, if any, in the given data? Very careful, we are talking about spatial heterogeneity, something that you have heard of and learned earlier. Okay, so again, I'm going to quickly write down, just visualize my data, because this will help me, move forward. P1 to Pn. It turns out that P1 is 1, P2 is 2, P3 is 3, P4 is 4, P5 is 5, P6 is 6, and so on and so forth, and Pn is n. Okay, they're asking me what is the estimator of mu p. Well, we have learned earlier the best guess of mu p from a given sample is just p bar, which is summation I equals 1 to n pi by n, and this is going to be nothing but summation I equals 1 to n I over n. Okay, interestingly, in the numerator I have the sum of n natural numbers going from 1, 2, 3, 4 till n, right? And we you must be aware from high school that this value is n plus 1 over 2, and there is an n sitting in the denominator, so I basically have n plus 1 over 2. This is n plus 1 over 2 is the sample mean and my best guess for what the population mean would be. Okay, now of course p bar itself is comprising pi's, which are random variables, so p bar is a random variable. If it is a random variable and I have a point estimate of p bar of p bar in terms of n plus 1 over 2, it comes with an error because random variables can take multiple realizations, right? So the idea is that, okay, if it comes with an error, how do I contextualize that error or come up with a 95% confidence band to have some level of certainty of what is the range of values that mu p can really take as far as its representation by p bar, right? So to evaluate the confidence band, to evaluate the confidence band of mu p, right, we need an estimate of variance of p bar. Okay, and the variance of p bar is nothing but variance of summation I equals 1 to n pi over n, and we saw this in couple of lectures ago that when you have spatial dependence, we can represent this variance as a covariance formulation, which is nothing but 1 over n squared summation I goes from 1 to n, summation j goes from 1 to n, covariance pi pj. Okay, and now to be able to sort of sum these covariances for all different combinations of I comma j. Remember, I can take value 1 and j 2 and vice versa. I can be 2 and j 1. So we have to double count these things, right? So what we really are doing here when we are evaluating this this double summation operator is basically we are counting all the elements in the variance covariance matrix. So this first step was very helpful, was indeed very helpful, right? So this will basically what I'm doing is I'm summing sigma squared in the diagonal elements n times. The off diagonal elements I'm summing 2n times because they appear twice on the right of the diagonal and the left of the diagonal. Okay, so I'm just going to follow that. I'm going to say 1 over n squared. I have n sigma squareds and 2n times sigma squared lambdas, right? And so I have sigma squared over n 1 plus 2 lambda. Okay. Now if pi's were spatially independent, lambda would be 0, and I would come back with, I will get back my sigma squared by n valuation. So by virtue of this spatial dependence structure and the degree of spatial dependence that is exhibited by this parameter lambda, there is a bias that is induced in the variance if we were to ignore the spatial dependence in these data. Okay, so if I have my variance of p bar, I can evaluate my standard deviation of p bar, which is sigma over root n times 1 plus 2 lambda the square root. Okay, and this will imply the 95% confidence band for mu p can be given as p bar minus 1.96 sigma over root n times 1 plus 2 lambda, okay, comma p bar plus 1.96 times sigma n times 1 plus 2 lambda. Of course, 2 lambda has a power of 1/2, which is as the square root of this value. So this is the confidence band, 95% confidence band of mu p. Okay, and obviously we know that p bar is nothing but n plus 1 by 2. So these things are this is something we have evaluated right on this page. Now the next question, the last part of this question says, how does your estimator depend on spatial heterogeneity? Now we had said that spatial heterogeneity is a pattern which represents long-term trend. For example, when we were looking at the real estate values across Delhi, we saw a low to high gradient from the west to the eastern part of the city, okay, or the National Capital Territory of Delhi, right? So what that would translate is that somehow spatial heterogeneity should be a function of I, right? It should be a function of location. And if you look at both p bar and variance of p bar, and by extension standard deviation of p bar and the confidence bounds, none of them depend on I. They are all independent of I, right? So what we see here is that p bar is independent of I. That is, it does not depend on the location. It is not varying by location. Okay, higher priced homes are not clustered at a given sort of location on this circle relative to lower priced home at a different clustered location, right? We do not have p bar as a function of I. Furthermore, variance of p bar and standard deviation of p bar are independent of I. and by extension, the 95% confidence bounds or the confidence interval for mu p is also independent. Well, it's not mu p, it's supposed to be p bar because mu p is a truth, it's constant, right? So the confidence interval will be for p bar. So that's something you can call a typo in the question, but I've corrected it here. Okay, so is also this 95% confidence interval is also independent of I. That means that our estimators do not depend on spatial heterogeneity. There is no impact of spatial heterogeneity on our estimators, right? So spatial heterogeneity emerges due to trends that are a function of I. None of our estimators are a function of I. Hence, there is no impact of spatial heterogeneity in these data. All right, so let's move forward. The next question is calculate the amount or the quantum of bias generated from not accounting for of spatial dependence in these data, right? So what is the amount or quantum of bias that would be realized if we did not, account for spatial dependence when the data indeed exhibited that structure? Okay, so and we are given that n is 100 and lambda can take various values from negative to positive, right? When I started this lecture I said lambda can take positive and negative values. So of course we can solve this problem for the for each case, but we can also solve it for a general case. So first of all, p bar remains n plus 1 over 2 with IID and spatially dependent data. Okay, that means no bias irrespective of lambda value. Lambda could be 0 or it could be a negative or positive value between -1 and +1, right? It will have no impact on p bar. Second, bias in variance of p bar. Well, there will be bias, and we saw on the previous slide, we can go back and check, where we said that in case of spatially independent data, the variance of p bar would be sigma squared over n, whereas here it's sigma squared over n plus sigma squared over n times 2 lambda, right? So we have sigma squared over n plus 2 lambda times sigma squared over n, which is the spatially dependent case, minus sigma squared over n, which is the spatially independent case. And hence the bias is 2 lambda sigma squared over n, right? And of course you can now put in lambda and n, and you can get these values. Similarly, bias in the standard deviation of p bar, this you guys can calculate. It's quite straightforward. And then finally the bias in confidence bounds will come from the bias in standard deviation, right? So bias in confidence bounds, well, more specifically 95% confidence bounds, will originate from bias in the standard deviation of p bar. I'm going to write this value and I'm going to let you verify it. I'm going to let you verify it. Okay, so this bias, when you eventually verify it, will come out to be 2 sigma over root n 1 plus 2 lambda to the power half minus 1 whole multiplied by 1.96. Okay. Okay. Now, of course, we have asked for these values at different levels of lambda. So, I can just provide, this value for the case for the variance. We have lambda, which has minus 0.7, minus 0.2, 0.4 and 0.9, right? And the bias in variance of p bar will be correspondingly minus 0.014 sigma squared, minus 0.004 sigma squared, 0.008 sigma squared and 0.018 sigma squared. So, I am writing corresponding bias values. You can go back and check at your in your time. Okay. Similarly, the bias here with lambda will be, lambda is all these values minus 0.7, minus 0.2, 0.4, 0.9, right? And bias in standard deviation of p bar will simply be, the first one will be a complex number. It's because it's a square root of a negative entity. So, minus 0.1 plus 0.06 iota times sigma, comma, minus 0.02 sigma, 0.03 sigma and 0.07 sigma. Okay. I strongly encourage that you go ahead and you verify these solutions. The bias in 95% confidence interval, as I've said, will simply originate from standard deviation of p bar. So, they will be simply these values, right. So, you can simply carry them forward to this case. Okay. Let's move forward to this circular city example, and we finally have this query where we are saying that what if we were to extend this first order spatial dependent structure to a second order spatial dependent structure. Not only that, where the strength of interdependence among the first order neighbors will be double the strength of interdependence among the second order neighbors. So now we are sort of relaxing this restriction that spatial spillovers or spatial correlation only occurs with the first order neighbors. We are saying that, well, it can also occur with second order neighbors. Okay, so we have a circle again. We have our P1, P2, P3, P4, P5, P6, all of these are equidistant. My figure is not to scale, so you shouldn't sort of, if some pairs look closer, they are not really closer, they are all equidistant. Okay, this case is slightly more interesting. It says that there will be a spillover on the value of P2 from P1 and P3, but also a spillover from Pn and P4. Although the spillover that is represented by these yellow arrows, which are from the second order neighbors, are half the strength of the first order neighbors. Okay, so let's try and exhibit this problem first of all in the variance covariance matrix. So we've solved this problem for the previous case, and we saw that the variance covariance matrix is really good in encompassing all these all this knowledge. So I'm going to write down the variance covariance matrix for second order neighbors, the variance covariance matrix for second order neighbors. Okay, I'm second order neighbors and first order neighbors. So we have neighborhood spillovers of the second order, right? So we are not just saying we are only second order neighborhood spillovers. That would be quite an unrealistic setting to work with. So here rho sigma p is nothing but you have your diagonal elements, which are simply sigma squared, sigma squared, sigma squared, keep going all the way to sigma squared. Okay. Now you have on the off diagonal elements, you have sigma squared lambda, and in the second order off diagonal element, you have sigma squared lambda by 2. Okay. And if I keep going forward, if you will realize that 1 will also have a spillover from location n minus 1. So you will have sigma squared lambda by 2 and sigma squared lambda to top it off. All others are zeros. Okay. Similarly, I can go ahead and fill up these these entities: sigma squared lambda, sigma squared lambda, sigma squared lambda. I have sigma squared lambda by 2, sigma squared lambda by 2, right? And sigma squared lambda and sigma squared lambda by 2, and so on and so forth, right? You're going to have for entity 2, you will have sigma squared lambda by 2 sitting here. Everything else will be zeros, right? So you sort of get a gist of how these things will look like. So you have sigma squared lambda by 2. This is for the nth entity. You have sigma squared lambda by 2, and all other are zeros. Okay. So you can sort of fill these things in and construct a variance covariance matrix. Again, the estimator for mu p is simply p bar, right? So again, the estimator for mu p is simply p bar, which is n plus 1 over 2, right? But variance of p bar will be different, right? So you know now that the variance of p bar is 1 over n square summation I summation j covariance pi pj, and what we said earlier is it is simply this entity double summation operator is simply summing all the elements in the variance covariance matrix sigma, right? So we are simply summing all these elements in the variance covariance matrix. Okay, and if you sum them, what you're going to have is 1 over n squared, sigma squared appears n times, sigma squared lambda appears 2n times, and sigma squared lambda by 2 also appears 2n times. So now your bias is going to be slightly more, that is, it's going to be 3 lambda. So in case of when there is no spatial dependence, it's sigma squared over n. In case of first order dependence, we had 2 lambda for first order dependent structure, right? And 1 plus 3 lambda is for the second order dependent structure. So as spatial dependence increases, the bias in the variance of z bar, and consequently in the standard deviation of z bar, in the confidence bounds of z bar will start to increase, which will the bias will enhance. So you will be penalized more in terms of your estimators or your the precision of your estimators if you start to ignore these biases or this spatial dependent structure. Okay, so this was a very interesting example which sort of transitioned us out of that one-dimensional analysis of spatial dependent structure and its implication, its consequences, to a two-dimensional structure, right? So we started out very simplistic understanding, we came to a little bit more sophisticated understanding, and going forward we will we will have a even more sophisticated understanding or of these entities. As a next step, which we will do as a separate part or portion of this lecture, I'm going to talk about Monte Carlo simulations, which is a numerical strategy to evaluate the bias in the variance, standard deviation, and confidence bounds of P bar when spatial dependence exists in the real estate market. And we do not have to rely on these analytical methods, which can be mathematically quite complex or analytically quite complex. We can fall back on simulations, and we will give you an example with the same setting that we are working with right now. All right, see you in the next part of this lecture.